Oh, I think we're about ready to get started. I would like to introduce our speaker today. His name is Walter Wegst, and he was on the NSAB for all 6 years, I understand. And we also have some other former NSAB members in our audience as well, I'm told. And you're Dave Herman, I understand, and you spent 6 years on the board as well, as chair and vice chair both. And then we have Walt's wife, Kathleen Peterson, and she was 6 years on the board as well. And you were chair as well, correct? Okay, it's wonderful. Wonderful, thank you for being here. Walt has a Ph.D. in environmental health. He's a certified health physicist. He has 40 plus years managing environmental health and safety programs at university and at the site in the early 90s. So without any further ado, I want to turn it over to Walt. Thank you for being here.
Thank you, Barb. I don't know, are you picking me up on this? Okay. All right, well, I gave this talk, I don't know, 3 or 4 years ago to this board, and I got asked if I would basically repeat it for tonight. It's a little different. I added a couple of things that weren't on it last time. But I guess we're going to learn a little bit about radioactivity and radioactive decay. What are you pointing at? Oh, well, I can move myself over here and then they can't see.
Can you hear okay?
It's a little garbled, but yeah, a little bit.
Okay, radioactivity and radioactive decay. The very important thing is that radioactivity originates in the nucleus of the atom. So you can't freeze the atom or evaporate the atom or have the atom combine with some other atoms into a chemical compound. You can do that, but it won't have any impact on the radioactivity. The radioactivity originates in the nucleus, and it doesn't know what the atom is doing. All right, this is the classic Bohr model of the atom. It is not a good, accurate description of what an atom looks like today. I mean, we know a lot more about it today than we did when this was developed. But this is good for this side of presentation. And with the nucleus, I think I'll use my own pointer. With the nucleus in the center, which contains neutrons and protons, and we'll talk a lot more about those in a few minutes. And then there's the electrons which circulate around the atom. It kind of looks like a little miniature solar system. And the shells around the atom, around the nucleus, there's the K, L, and M shell. You don't need to worry about that for tonight's lecture. The nucleus contains protons and neutrons. Protons have a mass of 1 on the atomic mass scale. They have a mass of 1. They have a charge of +1. Neutrons have a mass of a little bit more than 1 on the atomic mass scale, and I'll tell you why a little bit more than 1 in a few minutes. They have no charge, and AMU is atomic mass unit. Okay, now, in the tables, charts, and so forth that list the various elements, the number of protons is designated by Z. And this is a chart of the nuclides. And Z is up and down on that axis. That's the number of protons. If you change the number of protons, you change the element. The total mass of the nucleus, the total mass now is designated by A. So if we want to know the number of neutrons in the nucleus, we have to subtract from A, we subtract the number of protons, and that tells us the number of neutrons. And on this chart, the number of neutrons are on the horizontal axis. So we can look up any element and any isotope of an element, and I'll talk about isotopes in just a minute, on a chart like this, chart of the nuclides. Z this way, N that way. Now, if you change the number of neutrons in a stable nucleus, that generally makes it radioactive. If you add more neutrons or subtract neutrons, the nucleus becomes radioactive. Not in every single case, but almost. And then just our nomenclature, I used U-235 as my example throughout this lecture tonight. You're all kind of familiar with U-235, I would guess, uranium-235. And the nomenclature is uranium-235, that's the total mass of the uranium nucleus. And then the 92 in the lower left, that's the number of protons. And that tells you what the element is. So to a certain extent, the U and the 92 are redundant. If you know the nucleus has a Z of 92, you know it's uranium, especially if you have a chart like this to look it up on. Okay? All right, now this little example here, this is something new from the last time I gave this talk. If we start with the simplest nucleus, one proton, with then an electron going around it, one proton. So it has a Z of 1, a mass of 1, and that's what we call hydrogen. Hydrogen is the lightest nucleus there is. Can't be any lighter because it's only got one proton. And a common chemical compound from that is water, H2O. Now, if we add another neutron to that nucleus, we add a neutron. Now the Z is still 1. It's only got one proton. But now the mass is 2. We've added a neutron. And that configuration, we call that deuterium. And you can make water out of that too, D2O. And that's what we call heavy water. And you may have heard of heavy water. It's been used in the nuclear business a lot. Now, if we add another neutron, going on down, another neutron, we still only have one proton, but now we have a mass of 3. That we call tritium. And I know you've all heard of tritium. And tritium is an unstable form of hydrogen, and it has a radioactive half-life of 12.33 years. And we can make water out of that too, and we call that tritiated water. Now, down at the bottom, what I've showed you so far as I can remember, as far as I know, this is the only case where isotopes of an element have a unique name. This is hydrogen. We add a neutron, which makes a new isotope of hydrogen, but we have a new name, deuterium. Then we add another neutron, and we have tritium. Now, with all the other elements that are on here, we don't use a different name. We go back to the nomenclature I showed you on the previous slide, and we change the numbers, but we always call it uranium. It may be uranium-238 or uranium-233, but it's always called uranium. It's not a different name. Now, when this unstable nucleus decays here, what happens is one of the neutrons changes from a neutron to a proton plus an electron. Now, on my first slide, I said I'd tell you why the neutron is a little bit heavier than the proton. That's why, because the neutron is a proton plus an electron. So the electron mass adds a little bit to the proton mass, so the neutron's a little bit heavier than a neutron. And when it does that, this electron right here is ejected from the nucleus, called a beta particle. And now the nucleus is not radioactive anymore. And in fact, now the nucleus has 2 protons in it, proton, proton, and 1 neutron. So our Z has gone up by 1. The mass has stayed the same, 3. Now this thing is a new element called helium. Okay? And it specifically is called helium-3 because it has a mass of 3. Helium that's found in nature is helium-4. But they're both helium and they both behave chemically pretty much the same way. All right, this is just a chart, a small part of the chart of the nuclides. Let me pass these around and you can take a look at. This is the chart of the nuclides. This chart has a huge amount of data in it, which is of interest to nuclear physicists and nuclear engineers. But I just wanted to show you what it can look like. This is a chart of the nuclides. This is just half of it. The other half is back here. And these are then, if you go across this way, these are all the different isotopes of the same element. So here's, is that copper, I guess? All the way across here, these are all the different isotopic forms of copper. And the only stable one is right there. All the other forms, nuclear forms of copper, are radioactive. I just picked that one just as an example. That's true of most. Okay, now, all the elements with a Z less than 82, less than or equal to 82, Z equal to 82 is lead. And all the elements below that with lower Z have some stable form of the nucleus. But anything with a Z above 82, there are no stable nuclei that exist. Everything with a Z above 82 is radioactive. Now, uranium and thorium, for example, we say they have quasi-stable states because the half-life of uranium-238 is 4.4 times 10 to the 9th years, which is about the age of the Earth. But it's still radioactive. Okay? In fact, every isotope of uranium is radioactive. And every isotope, as I said, just to emphasize it, every element above 82 is radioactive, has no stable state. And I already mentioned that, I think. As we add more neutrons or subtract neutrons from the nucleus becomes unstable. Okay, now unstable nuclei have to get rid of their energy somehow. And they do it by emitting a particle. And they emit an alpha particle or a beta particle, not both, one or the other. And sometimes the particle emission is accompanied by a gamma ray emission. Now, you can't have a gamma ray emission from a radioactive nucleus without a particle emission. So you have to have an alpha or beta. Then you may get a gamma, you may not. And there's nothing special about the names. It's just the order that these particles were discovered in physics. The first particle that was discovered, they called it an alpha particle. The second particle that was discovered is a beta particle. Then they discovered that there was electromagnetic radiation, which is what this is, electromagnetic radiation that came off some of the nuclei, and they call that gamma radiation. Alpha, beta, gamma. Okay? Nothing special about those names. Now, as you will see near the end of my talk, for the case of U-235, almost all of the radioactive decays, in order to decay down to stable lead, most of the decays are alpha decays. Some of them are accompanied by gammas and some are not. Okay. If you have any questions, ask them. Raise your hand. I think we got lots of time. All right, now a little bit more about radioactive decay. An alpha particle is 2 protons and 2 neutrons, which if we were to look it up on this chart, we would discover that that's helium. I already showed you an example of helium that has 2 protons in the nucleus. So an alpha particle is a helium nucleus. Not a helium atom, a helium nucleus. And it has a mass of 4, 2 plus 2, it has a mass of 4, a charge of plus 2, 2 protons. And as I said, it's actually the nucleus of a helium atom. Now, beta particle's an electron, minus 1 charge, very little mass. Okay? 1/1800th of the mass of a proton. And that's the mass there, which adds to, when a proton and an electron get together and form a neutron, then this is the additional mass that causes the neutron to weigh a little bit more than a proton. Okay? Now, gamma ray is pure electromagnetic radiation. Let me see. The light here that lights up the room, that's electromagnetic radiation. Infrared heat is electromagnetic radiation. Microwaves, radar, that's all electromagnetic radiation. Now, gammas, as I mentioned, well, they have no mass and no charge. It's pure energy. A gamma ray now is exactly like an X-ray. Some of you may be familiar with X-rays. You probably all had some sort of diagnostic X-ray. Well, a gamma ray is exactly the same. It's just a little more energetic. And a gamma ray comes from the decay of a radioactive nucleus. X-rays come from, if you remember that slide I had up earlier that had the picture of the atom, with the nucleus and the electrons going around the nucleus. X-rays originate in the atomic structure. Gamma rays originate in the nuclear structure, but otherwise they're indistinguishable. If I have an electromagnetic radiation out here someplace, I can't tell you whether it's an X-ray or a gamma ray. And it doesn't make any difference because it's the same radiation. The only reason that we maintain the difference is to denote the origin of that wave. If you call it a gamma ray, then I know it came from the radioactive decay of a nucleus. If you call it an X-ray, then I know it came from the atomic structure of the atom. Okay? That's all. That's the only reason why we maintain those two names. And I indirectly mentioned this already, but if we have an alpha decay, then that changes the charge on the nucleus. And if we have a beta decay, that also changes the charge on the nucleus. And if we change the charge of the nucleus, what happens? We get a new element. And I showed you that with my little example of hydrogen, deuterium, tritium. It goes to helium. Okay, when the charge changes. And just in case some of you are frowning a little bit, when a nucleus emits a beta particle, that's a -1 charge. That means the net charge of the nucleus goes up by 1. Becomes 1 plus more than it was because it lost a negative charge. That makes sense to all of you? Yeah. Say that again. If
object is bombarded a large amount.
usually not with betas, but yes, it could happen with alphas. Yes. That wouldn't change. That's right. If if a nucleus absorbs a gamma, it doesn't become radioactive. But if it absorbs, and usually, I can't say this absolutely positively, but if it absorbs a beta, usually it doesn't change. It doesn't work that way. But if an alpha, definitely, and that's one of the ways that the early physicists discovered alphas, because they were using alphas to generate radioactivity in other alphas that came from radium. And at the time, they didn't know it was alpha, but they knew that the radiation from radium, if you used it to bombard something else, you could make the something else radioactive. But usually, the radioactivity, nowadays, we usually make radioactivity with neutrons. We bombard the nucleus with a neutron, typically in a nuclear reactor, and that's how we make it radioactive.
Can you hear me? I thought I was speaking. You qualified your statement on the beta with usually. Is there a circumstance where the beta particle will cause something to become radioactive?
I don't think so, but
Okay,
it's been a while since I studied my nuclear physics, but I don't think so.
Okay. Thank you.
Okay, now here is alpha and beta decay diagrammatically. Here's the original nucleus. Z is the what? What is Z? What? Yeah. And what else? It's the charge. Okay? If it's 30 protons, it has a charge of 30. N is the number of neutrons. Now, if a beta comes out of the nucleus, then the beta is -1 charge. So the charge of the nucleus goes up by 1. Z plus 1, or, okay? And then the number of neutrons goes down by 1 because one of the neutrons has converted to a proton and an electron, or a beta. The betas come out of the nucleus. So you have one less neutron, and that's a new element, Z plus 1. Now, in alpha decay, the alpha is 2 protons and 2 neutrons. So charge of 2 comes out of the nucleus. So the Z goes down by 2. And then the mass of the alpha contains 2 neutrons, which also come out of the nucleus. And so the number of neutrons in the nucleus goes down by 2. So the total mass of the nucleus goes down by 4 in alpha decay. Okay, now half-life. You've all heard of half-life, and you probably all know what it is, but if you start with 100 units, or 100 atoms, if you want 100 nuclei, 100 whatever, in one half-life, 50 of them will decay, and you'll have 50 left. That's half-life. Now, in the next half-life, half of these decay, which is 25. So now you have 25 left. Follow me? And then in the next half-life, half of these will decay, which is 12 and a half. So now you have 12 and a half left. And so this is what's called the logarithmic curve. And you don't get the same amount of nuclear decay every half-life. You get half of what you started with. Okay? Everybody follow that? Now, sometimes people say, well, this curve never goes to 0. You always have half of what you had left. Well, that's true mathematically. But if you look at half-lives, 10 half-lives, that's 1/2 to the 10th power. And that's 1 over 1,000, roughly. So if you wait 10 half-lives, you will only have 1,000th of what you started with left. And in many cases, for all intents and purposes, that's 0. Now, it's not if you talk about, well, it is for any a radioactive nucleus. But if you're talking about a radioactive nucleus that has a half-life of 25,000 years, you have to wait an awful long time to get to that level of decay. And then U-232, I don't know why that's still on there as an example, but uranium-232 has a 72-year half-life. Uranium-233 has a 159,000-year half-life. I'll talk about U-235 in a minute, which has still a longer half-life. I think that's left over from the last time I gave this talk. All right, here's the uranium isotope series. And again, I picked uranium not for any special reason other than that this body is concerned with uranium and what's left at the test site and so forth. And here's uranium-235. Here's uranium-238. And then all the different other isotopes of uranium. 235 is significant because it's the one that's fissionable. 235 is the isotope which is used in nuclear power reactors, and it's used in nuclear weapons, or it used to be used in nuclear weapons. U-238 is the isotope that is commonly mined because it has a very long half-life. As I showed you already, the half-life of U-238 is about the age of the Earth. So if that's the case, then half of what was originally formed when the Earth was formed is still here. All right? All right, now here's the decay series for uranium-235. And I put this up just as a typical example of how complicated the decay series for heavy isotopes or heavy elements is. We start out with uranium, and we want to get down here to lead, which is stable. So in order to do that, what happened? There we go. We have to go through all these different elements: thorium, palladium, actinium, thorium, a different isotope of thorium, radium, radon, polonium, and so forth. Here's lead, but that's radioactive lead. And then bismuth and tellurium, thallium, I guess, and then down to stable lead. And as I said, most of these decays are alpha, 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 alpha. All right? Some are beta, but most of them are alpha in order to get down to where it's stable. Now, if you look at this one, for just picking one of the as an example, palladium-231, an alpha decay takes away how much mass? 4. So we go down to 227. And then if we have a beta decay, what happens with a beta decay? Come on, somebody tell me. It doesn't change the mass, but it changes the what? The charge, the Z. So we go actinium-227 to thorium-227. We didn't change the mass, but we changed the element because we lost a negative charge. Okay? And this over here is just the abbreviations. There's this one here. The half-life is just 1.78 milliseconds. It decays very quickly. Here's this particular isotope. The half-life is 3.28 times 10 to the 4th years. The uranium-235 is 7 times 10 to the 8th years. So the isotope uranium-235 decays more rapidly than the isotope of U-238. But there's still U-235 left in nature from the original formation of the Earth because it has a very long half-life. You're frowning. Do you understand what I'm saying? Do you understand? Now, summarizing for the U-235 decay, there are 7 alpha decays in the chain. What's the mass of an alpha particle? 4. 7 times 4, 28. So to get from U-235 to 207, you have to drop 28 in mass. Okay? 7 alpha decays represent 14 protons offset by 4 beta decays. So a proton takes a plus out of the nucleus, a beta decay adds a plus to the nucleus. So if there are 14 protons that come out and 4 beta decays, that's a net change of 10 protons. Follow that math? All right, so we go from a Z of 92 to a Z of 82, which is what we had over here. U-235 down to plutonium, or lead, I mean. So we change the Z from 92 to 82. Now, most of the alpha decays, as I had mentioned earlier in my talk, are accompanied by a gamma ray. Not all of them, but most of them. And most of them are fairly, in this case, in this particular decay chain, most of the gammas are fairly weak gammas. But there's one in this transition here, which is, if I remember right, it's about 0.8 MeV gamma, which is a fairly energetic gamma. I don't need to say anything more about it. All right, now my last slide, just as this is an interesting sidebar. About 1.7 million years ago, the abundance of U-235 in natural uranium would have been 3% or higher than it is today, because it has a shorter half-life than uranium-238. So if you project the half-life curve backwards, then you would see the U-235 growing into your sample. And right now, U-235 in natural uranium is only about 0.72% of natural uranium. And that's not enough to have a self-sustaining nuclear reaction. And that's what they talk about when they enrich uranium. What they're doing is enriching this fraction of uranium-235 up to a point where the uranium can be used in a nuclear reactor or could be used in a nuclear weapon. Okay, now, that means that 1.7 billion years ago or so, the abundance of U-235 would have been high enough that if you added water to the mix, you could get a chain reaction. That was, some physicists calculated that, predicted that. Sometime way in the past, the uranium-235 abundance or percentage in uranium was rich enough that with water you could get a nuclear reactor. Well, sure enough, when the French, this happened back in 60s, I think, 1960s or so, when the French were exploring for natural uranium in Oklo, in the Gabon Republic of Africa, they found just such a nuclear reactor. They found a place where there was uranium deposit that had actually operated as a nuclear reactor, a self-sustaining chain reaction, and it operated for, I don't know, 1,000 years or more before it burned up all the U-235. The way they found it was because natural uranium, as I mentioned, has an abundance of U-235 of about 0.72%. But when they mined the uranium in this particular spot and measured for the abundance of U-235, it was less than what they expected. So they looked around a little more and said, hey, this was a reactor, what we call today a reactor. Now that reactor is estimated from measurements and stuff to have generated about 15,000 megawatt years. And for comparison, a large modern nuclear reactor generates about that same amount of energy in 4 years. So this natural reactor ran for quite a long time. And it produced all of the same fission products that a modern reactor produces. One of them is plutonium. I know you've all heard about plutonium and plutonium-239, and that's one of the things at the test site and so forth. Well, that plutonium was generated in situ, right there with the uranium. Nobody did any environmental cleanup, and that plutonium stayed right there. It didn't migrate out through the environment. It stayed right where it was produced, and it was locked up in the grains of the ore for a time comparable to its 24,000-year half-life. Now, plutonium has a very much shorter half-life than uranium. It's only 24,000 years, only. That's a long time, but it's much shorter. So actually, by the time they discovered this thing, that plutonium had pretty much all decayed. But they could tell it had been there by the decay products. Okay? And then at least half of the fission product elements were also immobilized in the geographic structure around that reactor, the geology around that reactor. It held all those fission products in place. And they didn't migrate out into the water table or any place. They stayed right there. This is the first one that was found. Since this one was found, as I say, I think that was back in the 1960s, people have looked for other natural reactors and found a number of them. I don't know how many, but there's been a number of other places identified as having been natural nuclear reactors that occurred, what did I say, 1.7 billion years ago, somewhere around then, 2 billion years ago. So we didn't discover anything when we discovered nuclear fission. Nature knew about it all along. Okay, that's kind of what I got to say. Got lots of time to answer questions if you'd like.
I forget, I should know, but I forget. What's the percentage you have to raise the uranium up to before it becomes fissionable?
I think the minimum is on the order of 3%. Now, that's not anywhere near high enough to make a weapon out of, and it's not as high as what they use in nuclear reactors, but it is high enough that under the right conditions you could make that when you say fissionable, any U-235 is fissionable, but if you want to talk about a sustained fission reaction, you need about 3% minimum.
Okay, how much do you need to actually make a weapon? Or what percentage?
More than 90%.
That's what I was thinking, yeah. That's
and if I knew the number, I couldn't tell you.
I don't remember either.
It's more than 90%.
I'll call Iran, they know what it is.
No. No. That's what I tried to say, and maybe I didn't say it real clearly in one of my early slides. The half-life, the radioactivity is associated with the nucleus, not the atom, the nucleus. And there's no way that we know of to date, and there's no way that physics predicts that you can change that. You can't accelerate it, you can't slow it down, you can't put that nucleus into some kind of chemical form that would change. You can't. You can't. Yeah.
What is neutron?
What? What is neutron radiation? I'm not hearing you.
What is neutron radiation? Is there such a thing?
Well, I showed you neutrons. Oh, I see what you're asking. Neutrons come from, neutron radiation comes primarily from a nuclear reactor. And when a nucleus splits in half, when it fissions, and that's another whole lecture, but when a nucleus fissions, it releases a lot of stuff, including neutrons. And then you get neutron radiation. Now, neutrons also come from outer space. You also get some neutron production from cosmic rays that interact with atmospheric molecules and release neutrons. But you don't get neutrons from radioactive decay. Okay, does that answer your question?
Neutron radiation from actual fission.
Yes. Yeah. Now there are some neutron generators which can produce a beam of neutrons that don't use fission. And you can do that with a tritium target. Remember tritium from one of my early slides? You bombard tritium with deuterium, I think it is, you can cause the emission of neutrons, and you can get a beam of neutrons out of this accelerator. Okay. But in general, neutron radiation comes from fission.
Bill, can you use the microphone, please? Please talk
Going
right
back
into
to my
it.
question earlier, so there really is no way to slow down radiation except to encapsulate it. In other words, I guess what I'm trying to get at is I've heard that some of the European countries have been able to reduce the risk of radiation, and my other question was there a way to do it? And you said no. So, but the only other way then is to encapsulate it so that it doesn't emit. Am I right?
Sort of. If you're talking about fission products, and I think you are, from nuclear reactor waste, you can encapsulate them, you can put them in some kind of a shielded container, and you then absorb the radiation before it can get out into the environment. But you don't change the radioactive decay. All you're doing is putting it in a package where the package prevents the radiation from getting out into the environment. Right?
That's the only way.
Yeah, it's the only way. Now,
Microphone, please.
this may be, yeah, go ahead.
Well, I think what Bill is trying to get at is that radiation is one thing and radioactivity is another. Radioactivity causes radiation. Radiation is nothing more than like radiating down on us. But the light's up there. So you can't change the light. Block the radiation, for example. I'm now shielded from that.
Well, yeah. Cosmic rays, you've all heard of cosmic rays. Cosmic rays are a form of radiation. Fortunately for us, the Earth's atmosphere blocks a lot of those cosmic rays from reaching this level of the Earth. They're stopped by the atmosphere. That's called a shield. What you're talking about is called a shield. You put the radioactive material in some kind of a container, which is a shield, and it then absorbs the radiation. Not the radioactivity, but the radiation.
All righty. Thank you so much, Walt.